us to visualize that if we hide one of these sets. So I'm going to use a handy tree that's made by Quick Split, where I have display control to turn these sets on and off. So let's look at some parting surface creation options. And the first one we're going to use is called external. It's really ideal for parting lines because it spreads out from the part edges, but it stays as flat as possible to the draw direction. So in the beginning here, I'm going to change some edges. And then I need to fix the vector direction. 0 indicates draw. Now the distance I'm going to enter here is only really important in that it goes out past the eventual size of the cavity block or the plate that we're going to cut from. For our case, 4 inches is going to be enough. And you see the result. You see how it radiates out. It makes a really nice, smooth parting face. Another type of surface is sweep. And sweep doesn't spread out. It just goes in a straight direction. But sometimes that's exactly what's needed, like on the end of our part here. Now, our part is symmetrical, which means we can take advantage of a mirror function and copy some parting surface over to the other side. A lot of plastic parts are like this, as you know, or even parts that are left hand and right hand. So mirror has to be a handy tool in the system. And another handy tool has to be strong ability to trim faces. When you're working with surfaces, either in the part itself or on the parting like this, the ability to quickly trim them anytime is a must. And this is something that Cimatron has always excelled at. So we trim those off to each other. If we look at this last area then, I'd like to fill in this gap with the smoothest surface possible also. And this time the surface type I'm choosing is a blend. A blend is a very powerful optional step that's going to bridge an area, but it also precisely follows a guide curve. So, if we show the rest of the part again, what I'll do next is assign some status to the surfaces that we've made. What I'm going to do, I'm informing the system that these are the parting lines. And it's also very nice to see how a copy of the parting faces will move along with the part. You can really kind of see what the cavities are going to look like at this point. So now, even though the parting on around the outside is defined, there are still many open areas in the middle of the part. Sometimes these internal shutoffs are easy to fill. Other times they can be quite complicated. So for the easy ones, Cimatron has a tool that just seals them off. What I'm going to do first is ask the system to identify all these simple internal loops. Now we saw how the external surface worked. So here we're going to use the internal surface command. It seals off any of the flat or the contoured areas that we ask it to do, really in one click. And this can be a huge time saver for parts that have a lot of internal islands. Now, more difficult areas need something else. And Cimatron has a very smart extension function called close open faces that we want to look at next. And it works on open solid technology. So what I'm doing here is first I'm unstitching the faces I want to work on from the rest of the part. The rest of the part being the blue area that currently is hidden. So the close open gaps function, it works by selecting an internal loop. Then all of the boundary faces are extended out to meet each other. And this function is doing amazing things that we've seen in shut-off areas that used to take a lot of time to extend and design. Now, like before, we want to assign these internal surfaces as parting, so we can visualize a copy in both halves of the mold. And that really leaves only two windows in the part that I've left undefined here. But I'm going to leave those open for now to save time, but also to show how Cimatron can keep moving ahead in the design process without worrying about gaps or undefined areas like this. And I can come back to the parting area anytime for changes or adjustments, but really the next move is to work on the mold itself by creating the cavity blocks. So I'm going to use an export function. I'm going to ask that the new part be called core, and that it be located in the movable side assembly of our project. And here's where the knowledge I assigned in the quick split function really pays off. So you see how it knows all of the data that's in the lower set that needs to go out to the core block. So here's the new part core with the part surfaces in it, but it's not the end, of course. We still need to define the core block size, and that can happen now. What I'll do here is I'll use the sketch environment to design a centered box that will then extend into our workpiece. Now this solid then, it represents the workpiece block. It's going to surround the part. This will be the stock that we're going to trim off by those parting surfaces that we just made. So another export utility. And again, we're going to see how that work that we did in Quick Split pays off again. The system knows any parting faces that belong to the side we're working on. And you see here how they're lighting up as kind of a visual check that things are as we expect them to be. And then lastly, an arrow which shows the part of the stock that's being cut away for a finished core block. There probably isn't a simpler way to build a mold cavity from a part. It's the parting faces that cut the solid block, just the surfaces we built. The part itself, whether it's good data or bad data or with unfinished shutoff like we have here, it just comes along as is. The whole core block can be described as kind of a hybrid solid model. We can do anything to it. For example, a few rounds on the back edge are no problem. Cimatron does all kinds of operations using the speed of solid modeling, but without wasting time with a restrictive requirement for perfect geometry. I think it's now time to get a mold base involved in the design process. Cimatron ships with over 20 catalogs from all over the world, and adding a mold base is a catalog operation. Here we're going to use a PCS standard configuration. On screen, what we'll see is a preview of the mold as we make decisions to the size. And to determine the X and the Y, if we'd like to, what we can do is ask the system to choose the best fit for us based on a minimum stock we want to keep around the cavity blocks. The plate thicknesses, they're standard but adjustable as well. So, as mold-based parts are created, we're going to see them entering into the assembly tree over here on the left. The system knows which plates, which components belong in which area of the mold design. And the entire mold assembly being created right now is associative, of course, so it's editable at any time.
I think one of the things to note also is you pick the standard from a standard mold base from PCS. You can also go ahead and pick that mold base, and then you can go non-standard and type in any of your sizes, whether it's length, width, or an odd-sized plate. You can go ahead and put that in as well, too.
Now what we're going to do is we'll be looking at some very specific functions in Cimatron that are just for mold design. But first, what I'd have to do is add a few more parts here. And I'm going to start by placing our second core block into the design. What this will be is an associative copy of the first block. In other words, the same part in two locations, so that any change to the one will affect the other as well. And again, we're using those original layout points. And what that does is it keeps the cavities connected for easy adjustment later on. And we're also going to create a runner block for this side of the mold. It's very easy to pick up contours or reference other parts while working in Cimatron. And any reference between parts is associative. So which means that the whole design is going to be able to update and adapt as the changes come along. And also a pocket in the B plate is needed. That's the last thing I need to do here. And again, we can use the references from neighboring components in the design.